defined by phi. And that's biholomorphic onto the moduli space of rank 2 degree d sigma semi-stable pairs. Okay, so it precisely hits the sigma semi-stable pairs, where sigma is determined by tau. It's half the degree minus tau, and I have to tell you what sigma semi-stability means. Okay. Okay, so stable pairs. So this is the key definition. So let's fix a positive number sigma, and we're looking at rank 2 degree d holomorphic pairs E phi. Okay, so such a pair is called sigma semi-stable if the following is true. So first of all, for every line bundle f contained in E, the degree of f is no bigger than half the degree of E, so d over 2, plus sigma. Okay, so if sigma weren't there, if sigma was 0, this would be saying that the bundle is semi-stable in the sense of just bundles rather than pairs. But we allow a bit more wiggle room because there's this sigma, which is positive. However, if it happens that phi is actually a section of this line subbundle f, we then impose a sharper condition. In that case, we require that the degree of f is at most half the degree minus sigma. Okay? So, and sigma stability is defined by the same conditions with strict rather than non-strict inequality. Okay, so these are conditions that come out of a geometric invariant theory approach to such problems. So it turns out that there are of course moduli spaces M d sigma of such pairs. In fact, nearly always they're fine moduli spaces. They have universal families. It's convenient to fix the determinant of our vector bundles. So what I'm going to do is I'm going to fix some line bundle lambda, or holomorphic lambda, line bundle lambda of degree d, and insist that lambda 2 of E, the exterior square of E, is isomorphic to lambda. Okay, so that defines this space M lambda sigma. So it depends on this line bundle lambda, but mostly only on its degree and on sigma. Okay, so Thaddeus back in '92 gave a beautiful and very precise description of these spaces, and I'll review that. And it's these compact Kähler manifolds M lambda sigma. They come with Kähler forms. They're compact. They are smooth. There are no singularities in sight. Those are the subject of this lecture. So this lecture is about the proposal that certain spaces of this type are interesting from the point of view of Floer theory and as homes for Floer theoretic invariants of 3 manifolds, analogous to and to instanton Floer, but perhaps, if it works at all, circumventing some of the difficulties with singularities and reducible connections that appear in instanton theory. Okay, so yeah, let me talk a little bit about gauge theory and symplectic geometry. This is a topic that one could talk about for a while, so I'll keep it brief today. So the equations that I've been discussing, so flat connections, rank 1 vortices, they appear as dimensional reductions of equations over 4 manifolds with 4-dimensional gauge symmetry. So flat connections, that of course is the reduction of the instanton equation, while the vortex equation is essentially the dimensional reduction of the Seiberg-Witten equation in the presence of a closed but not exact two-form perturbation. That two-form, is the one that has to restrict to this two-form eta that I had, which had positive area on my surface. The rank 2 vortex equations are essentially the dimensional reductions of four-dimensional non-abelian Seiberg-Witten equations, which have been studied by Fichen-Lannes and various others. Okay. It's a slight oversimplification to call them the dimensional reduction, but let's go with that. So, of course, instanton and Seiberg-Witten equations give rise to invariants of 3 and 4 manifolds, and the invariants for those 3 and 4 manifolds that contain this surface Z are intimately related to symplectic topology on the Kähler manifold in question, so the moduli space of projectively flat connections or the symmetric products. So they're intimately they're intimately related both to Lagrangian submanifolds, so bounding 3 manifolds give rise to Lagrangians in these things, and to holomorphic curves. When D is an even number, the space of projectively flat connections is singular and problematic for Floer theory. So way back, the proposal of the Atiyah-Floer conjecture was to relate instanton Floer homology for 3 manifolds with Heegard splittings to Lagrangian Floer theory in such a moduli space, but it's really hard to make a precise statement. Moreover, the instanton Floer theory for 3 manifolds is itself hard to set up beyond a rather restricted case of homology 3 spheres because of difficulties with reducible connections and associated singularities. So our aspiration is to use a certain space of stable pairs, M lambda sigma, for an even degree D as a substitute for this moduli space of projectively flat connections, and to construct 3 manifold invariants via Floer theory in such a space. It remains an aspiration. It's not one we have achieved so far. But I emphasize that this is a case where one doesn't really know how to do things in the instanton theory because of the singularities. Okay, so let me talk a little bit about what these spaces M lambda sigma look like. So this is Thaddeus's story. Okay, so I've repeated the number E. To say that E phi is sigma semi-stable means that for every line bundle F contained in E, its degree is at most half of D plus sigma, but there's a sharper condition that the degree is at most half the degree minus sigma if it happens that phi is actually a section of your line subbundle. Okay? So of course this condition depends on sigma, but not that much. I mean, if the numbers are in question are always, the degree is an integer. D over 2 is also an integer if D is even, and so wiggling sigma a little bit won't change anything typically. Okay. So for convenience, I'll take D positive or non-negative and even. Okay, so let's contemplate a sigma semi-stable pair. Now, it's not difficult to show that phi is always a section of some line bundle F sub phi contained in E. Okay, you can cook up such a thing fairly simply, and let's take it to have maximal degree. So that line bundle possesses a section by definition, and so it has non-negative degree. That condition already forces sigma to be not too big. Sigma is at most d over 2. In other words, these spaces become empty if you exceed that bound. So what happens is that you get a sequence of non-empty moduli spaces, mi, and so mi is, perhaps it's, it's kind of hard to digest when it's written in the middle of a dense slide like that. Let me just write it again. So mi is, so this is sort of as big as sigma can be. So I subtract integers from it, and then a little bit more. Okay. So epsilon is between 0 and 1. Okay. So let's think about m0 first of all. Well, in m0, in m0, this inequality here. Sorry.
This value is the value of sigma.
This is of. That's right. That's sigma. That's sigma. So yeah, this one here. So when sigma is, so in m0, that means sigma is very close to d over 2, and so that means that the degree of fi is just forced to be 0. So in other words, fi is a degree 0 line bundle with a section. There are not very many of those. It follows immediately that fi is trivial, and phi is a trivializing section. So in other words, fi comma phi is a whole degree 0 and rank 1, and it can only be the trivial pair, so OZ, the structure sheaf and 1. Now, your rank 2 vector bundle E, well, it contains this as a subbundle. The quotient, the determinant is fixed, and so the quotient can only be lambda. So in other words, E is an extension of OZ by lambda. Okay. Well, you look a little more at the defining inequalities, and you see that it cannot be a split extension, because if it were, then you would get a line subbundle of too big a degree. But it turns out that's the only constraint. So in other words, an element in M0 is basically determined by an extension of the trivial line bundle by lambda. And so such extensions are parameterized by h1 of lambda inverse. When you think carefully about the equivalence relation, you see that the right thing to look at is the projective space on that. And so that's what M0 is. It's just a projective space. Okay. Said dually, I can think of it as the projective space on the dual of sections of K0 of the canonical bundle tensored with lambda. Okay. So that one is very simple. M1 is slightly more complicated, because in that case, Fi could have degree 1. So it's possible that Fi with phi forms a degree 1 holomorphic pair, and such pairs trace out a copy of your curve Z. And it turns out that M1 can be described as the blow-up of M0 along a copy of Z. And if I think of M0 like this, then it's just the blow-up along the copy of Z that's embedded as the linear system Kz lambda. Okay, so Z embeds into this space via the linear system Kz lambda, and so that gives a curve in this space, and you blow it up. Okay. And that's M1. And thereafter, so we have M0, we have M1, which sits over it as a blowup, and then there's a whole series of spaces, and it turns out that they're related by rational transformations, more precisely by flips. So M1 differs from M2 by but it only differs along oops. Sorry, that's what happened. I turned my clicker upside down. So while M0 and M1 differed by essentially in codimension 1, these two only differ in codimension 2. And codimension 2 is the difference between successive spaces, all the way up. So they differ by flips. There's a quite precise description, and I'm not going to say more about what that is. But Thaddeus makes it very, very explicit. So one thing so all of them are smooth and projective. From this description, you can actually rather easily see the dimension. It's d plus g minus 2. G is the genus. They're certainly simply connected because, after all, they're birational to projective space. And for I greater than 0, the Picard group has rank 2. So the second cohomology is z squared. Okay. So and the one that's going to be our focus is the last in the line, what I've called already in what I wrote on the board, M top. Okay, so that's M d over 2 minus 1. Okay, so what that means is that sigma is small. Sigma is between 0 and 1. So that's the space of semi-stable pairs in the following sense. So E is a semi-stable vector bundle. And F phi, this line subbundle that contains phi, does not destabilize it. So it's a semi-stable bundle, so it might be strictly semi-stable. And that's so in which case it has some destabilizing line subbundle, but that one is not allowed to contain phi. Okay? So the key thing about this one is that it comes with a map to the space of semi-stable vector bundles. I call it an Abel-Jacobi map. Yeah.
No risk of destabilization, right?
Well, let's just make the blanket assumption that D is even. Okay. There'll be sort of mild changes if D is odd, but I'm not going to think about that case. Okay. So there's this Abel-Jacobi map that sends E phi to E. Its fibers are the projective spaces of sections. So the fiber over E is a projective space on H0 of E. And so I want to think of the Abel-Jacobi map as defining a kind of resolution of this singular gadget, this singular moduli space of semi-stable bundles. It's not truly a resolution in the sense of algebraic geometry, but it's something like it. So it's at least smooth. It lives over n semi-stable. And provided that the degree is reasonably large, at least 2g minus 2, the Abel-Jacobi map is surjective. And so it's something like a resolution, but it's higher dimensional. Okay. So I want to focus on M top, because that's the one that's close to the world of stable bundles and flat connections, which is what we know is a good hunting ground for interesting 3 and 4 manifold invariants. Okay, so we still have another. I've argued that the parameter sigma that I want to look at is the one where sigma is small. We have another parameter to fix, which is the degree d. Well, if you think about Heegaard-Floer theory, so that's based on sim d surface z, but with a specific d, namely d is the genus. And the reason for taking d equal to g is that in that case, if you have a handle body bounding your Riemann surface, okay, so this is now sort of solid, then that handle body defines interesting Lagrangian submanifolds of sim G specifically. So these Lagrangians are, so they're tori. You can construct them very simply and explicitly, as Oshvat and Zobo did, as the point in the G-fold symmetric product consisting of one point from each in a G-tuple of disjoint circles that bound in the handle body. That locus can be understood as a Lagrangian with respect to a suitable Kähler form. Or you can also construct them implicitly in two ways, either as limits of solutions to the Seiberg-Witten equations on, well, almost on the handle body. More precisely, you need to cylindrically complete the handle body, and also you need to puncture it somewhere. And one uses Taub's type perturbations. There's also another way of obtaining these Lagrangians implicitly as iterated vanishing cycles for degenerations of symmetric products. Okay, so D equal to the genus is sort of important for Heegaard-Floer theory because it gives rise to Lagrangian submanifolds. So I'm not going to fully flesh out the following claim, but my claim is that when one is thinking about rank 2 stable pairs and the rank 2 Seiberg-Witten equations over handle bodies, the right degree to look at is D equal to twice the genus plus 2. Okay, so somehow that's going to be the one where it's sensible to look for Lagrangian submanifolds. So to say, I'm not going to really justify that claim in this lecture. But let's look at that. So from now on, mz is m top for a fixed determinant lambda, which has degree 2g plus 2. Okay, so this turns out to be smooth projective of complex dimension 3 times the genus. Okay. So there were reasons to select sigma small, namely that takes us close to the world of instantons. And there was a reason to take degree 2g plus 2, which is that it's a sensible place to look for Lagrangian submanifolds. And now there's a nice observation, which is that in that case, mz turns out to be a Fano manifold. So monotone as a symplectic manifold. And this is absolutely specific. So for example, if I fix the degree, there can be at most one range of sigma, one chamber of sigma, for which one gets a Fano. And in this case, it's the top chamber. So of course, simply connected Fano manifolds are a very nice place to try and do Floer theory. Okay, so this is the dream. The dream is to construct a non-abelian Heegaard-Floer theory based on this space mz, this Fano 3G dimensional manifold. If you have any pair of simply connected embedded Lagrangians, I should have said that with the same numerical count of Maslov 2 disks attached to them, they have a well-defined Floer cohomology. Okay, so it's defining Floer cohomology is really very unproblematic in this situation. So the conjecture, and I, at this point I'd hope to be able to report this as a theorem, but we've made progress on this but have not proved this. The conjecture is that a handle body U bounding Z will define an embedded Lagrangian submanifold in this moduli space, diffeomorphic to the product of G three spheres. Okay. So that's supposed to be an analog of the Heegard tori. Okay. So if that were true, you could use them to form a Heegard-Floer type theory for three manifolds based on the Floer cohomology for the pair of Lagrangians that you get from a Heegard splitting. Okay, you would need to think, of course, about their stabilization invariance. So when the genus is 1, so then the degree is 2 times 1 plus 2, so it's 4. So in that case, MZ is just M1. It's the blow-up, actually, of CP3 along a copy of Z that's embedded in CP3 via degree 4 linear system. Okay? And in that case, the conjecture is true. So in that case, one is asking for Lagrangian three spheres attached to bounding handle bodies. And one can construct those just as vanishing cycles for a Lefschetz pencil with fiber MZ, which is easy to exhibit. Okay, so we haven't got there yet for genus greater than 1. We have a couple of strategies. Okay. So that sort of concludes the part of the lecture that's about aspirations. And now I'd like to tell you what we can actually do. So gauge theory has a symplectic interpretation on fibered three manifolds. So you have a three manifold Y with a submersion to the circle. So the fibers are surfaces, and this is the situation where we can actually get some results at this point. So let's say Z is the fiber, and phi is the monodromy. So one thing one can do in this situation is as follows. So if you fix a non-negative number D, so phi can be made to act symplectically on the d-fold symmetric product. And there's then a symplectic fixed point Floer homology for that action. And that has a gauge theory interpretation as a summand in monopole Floer homology, Seiberg-Witten monopole Floer homology for your fibered three manifold. The summand just corresponds to a subset of the spin C structures determined by D. So that principle suggests that it's worthwhile taking a look at fixed point Floer homology for the action of the monodromy on this space of rank 2 stable pairs that's of interest. Okay. Now in this setting, it's of interest to take any degree D, but I'm going to focus on the one that I already identified, because I've sort of argued that the Fukaya category of that one, of MZ, is of interest, and so we're going to focus on that, on fixed point Floer homology inside MZ. Okay. Okay, so through fixed point, familiar to many in the audience. So I'm going to describe a fairly simple dictionary. So one can think of the following data. So you take a compact symplectic manifold M omega together with a symplectic automorphism phi. Okay, so I've written that in red, and subsequent things written in red are related to that. It's equivalent. There's an equivalence of categories. It's equivalent to think of the following data that I've written in blue. You take a proper fiber bundle, T over the circle, together with a two-form capital omega on it, on its total space, which is closed and which is fiber-wise symplectic. The way that this correspondence goes is as follows. If you're given this symplectic automorphism, you form its mapping torus, T phi. Okay, so you know that's this quotient of M cross R by, you know, where you sort of you wrap it around and force the monodromy to be phi. And this closed and fiber-wise symplectic two-form omega sub phi, which is just characterized by saying that up on M cross R, it's the pullback of omega. Okay, so in that direction, you take this compact symplectic manifold and an automorphism, and you build this fibration over the circle. In the other direction, if you're given such a fibration over the circle, you can take its fiber to get a symplectic manifold, and its symplectic monodromy to get an automorphism thereof. So symplectic monodromy means that you use the natural symplectic connection, whose horizontal spaces are the complements with respect to the given two-form to the vertical tangent spaces.
That P phi should be maybe inclusion map, because
Sorry.
P phi is star of omega phi.
Yeah, so what did I write? P phi. Oh, I'm sorry, you're right. It should. So what it's supposed to be, it's not the right. Yeah, you're correct. That's the type. So all it's supposed to be is the following. It should just be this one. Thank you. Okay, so under this equivalence, fixed points of phi are the same thing as horizontal sections of the corresponding bundle. More subtly, the following is true. So you can, if you start with this bundle over the circle with this given two-form, you can perturb the two-form by adding to it another two-form eta that's closed, and I'll take it to be 0 on the fibers. So it's more or less the same as a family of one forms parameterized by the circle with certain properties. Okay, so I'm going to add eta like so. So that changes the monodromy, and that change can be thought of as determining a symplectic isotopy in the monodromy, so phi t. That's the one that's generated by the, so eta sort of amounts to, like one forms a sub t wedge dt, and those one forms give rise to a symplectic isotopy. And in particular, it's of interest to look at the case where eta is an exact two-form on T, and that corresponds to the case where the flux in the isotopy is in the image of 1 minus phi 0 star. So exact perturbations eta correspond to isotopies with some condition on the flux, determined by a subgroup of the first cohomology, which can be non-trivial. Okay. All right. So fixed point Floer homology. Well, so if you have a monotone symplectic manifold and a monotone symplectic automorphism, so one such that the corresponding the corresponding two-form lies in a cohomology class proportional to the Chern class of the vertical tangent bundle. It has a fairly simply defined fixed-point Floer homology, HF of M and phi. It's a finitely generated abelian group. It's mod 2 graded. It's graded by the I'll come back to that. Its Euler characteristic is the Lefschetz number. It's a modulo over quantum cohomology. the reason for this business about flux, the reason for talking about that, is that this theory is invariant under isotopies phi t, which satisfy that flux condition that came up in the last slide. So in particular, it's invariant under Hamiltonian isotopies, but more is true. Okay, so if phi has non-degenerate fixed points, its fixed point Floer homology is by definition the homology of a chain complex CF phi that's generated over Z by those fixed points, with a mod 2 grading given by their Lefschetz signs. The matrix entries in the differential count J holomorphic sections of, well, the mapping torus cross R thought of as a fiber bundle over a cylinder. Okay? So provided that those sections have finite energy, they then have well-defined limits at t goes to plus or minus infinity, t is the r coordinate, and those limits are horizontal sections, or equally fixed points of phi. Okay, so let's talk about monodromy on stable pair spaces. So I would like to say that the mapping class group of a surface Z acts symplectically on the space of stable pairs. It's not precisely true. So here's what's true. So there's a central extension of the mapping class group that acts. So so gamma is the mapping class group. It has this extension gamma tilde by the first integer cohomology, and it's simply the following. It's the isotopy classes of pairs where phi is a self-diffeomorphism of your surface, and phi tilde is a linearization of that in the line bundle that you have selected. So it's an isomorphism of lambda with phi star lambda. Okay. So let's make Z into a Riemann surface. Let's make lambda into a holomorphic line bundle, and then we have this space M of sigma stable pairs with determinant lambda, and we fix some Kähler form in that. And then I claim that you can then construct an action of this extended mapping class group in the symplectic mapping class group of the space of stable pairs. And it's quite simple to do. You use this linearization phi tilde to build a line bundle over the mapping. So you then choose a fiber-wise complex structure in that and a fiber-wise holomorphic structure in this line bundle. And so, in other words, you build yourself an associated bundle of stable pair moduli spaces over the circle. Okay, so you start with, you think of phi as determining a bundle over the circle with fiber or a surface. You build an associated bundle with fiber, the space of stable pairs. You choose a fiber-wise, closed and fiber-wise Kähler 2 form in that bundle that extends the given one. And it turns out there's various ways about how to do that, and you take symplectic monodromy. Okay, so that's what determines this homomorphism mu from this extended mapping class group to the symplectic mapping class group of M. Okay, so we can then define stable pair Floer homology. So let's take this specific degree, 2g plus 2, and omega m an anti-canonical Kähler form. And so capital phi is this homomorphism applied to an element in the extended mapping class group. And so HSP of that is defined to be the fixed point Floer homology for that action. Okay, so it's this measure of homological measure of symplectic fixed points of the action of phi on the stable pair space. Okay, so it's a module sorry, it's an abelian group that's Z mod 2 graded and is a Z mod 2 graded module over the quantum cohomology of M. In particular, it breaks into generalized eigenspaces for the action of the Chern class of M. So it's a sum over lambda of these generalized eigenspaces for the action of the Chern class. So these summands can only be non-zero when lambda is either 0 or else an eigenvalue of C1 of M acting on the quantum cohomology itself. Okay, so let me tell you about so we're going to focus now on the genus 1 case. So in the genus 1 case, we can actually compute. So Z is now an elliptic curve, and MZ is the blow-up of CP3 along that elliptic curve, embedded via degree 4 linear system, or if you like, as embedded as the intersection of two quadric surfaces inside CP3. Okay. So the quantum cohomology of this space is not so difficult to compute. It turns out to be the following. It turns out that the eigenspace decomposition for the first Chern class acting on quantum cohomology looks like this. So there's a summand for lambda equals -1. That's 4-dimensional. And then there are 4 lines with eigenvalues 0, 8, -4, plus or minus 4i. Okay. The interesting part is the -1 summand. As an algebra, that part of quantum cohomology is isomorphic, quite non-trivially, to the cohomology algebra of Z itself. Okay. Reduced mod, gradings reduced mod 2. Okay, so as algebras, the quantum cohomology is the cohomology of Z plus a semi-simple part, C to the 4th. Okay. By the way, these, while this comes from a direct calculation, these numbers 0, 8, -4, plus or minus 4i can also be obtained via mirror symmetry using the Horry-Waffer Giventhal mirror superpotential. They do agree with what that gives.
So is there really a -4 plus 8?
Yeah. That's what we got. Okay, so now here's an actual result. So for Z an elliptic curve and phi in the extended mapping class group, there's a condition which I'll explain in a moment. So first of all, the stable pair Floer homology breaks up as its -1 part, the part where C1 acts as essentially as -1, more precisely the -1 generalized eigenspace, and then a boring part which is just Z to the 4th in even degree, okay, corresponding to all the other eigenvalues. So the interesting part is the -1 summand, and that is isomorphic to the fixed point Floer homology of the action of phi on Z itself. Okay, so in other words, the interesting part of fixed point Floer homology acting on this blow-up of CP3 is isomorphic to the fixed point Floer homology acting on the curve itself. Okay. The condition is homological non-degeneracy, which simply means that phi star -1 acts invertibly on the rational first cohomology of Z. It's just saying that phi is not a power of a Dane twist. Okay. This seems to be just a repetition that shouldn't be there. Okay, so a couple of notes on this. This fixed point Floer homology of the action of phi on Z is easy to calculate. It's free abelian on F, where F is the following thing. So you take the integer lattice H1 of of z with integer coefficients, and you look at the pre-image of phi star minus 1 of that lattice modulo that lattice. Okay, so it's easy to calculate. It lives in just one parity, which is given by the sign of the determinant of this one. And according to Yi-Jen Lee and Taubes, it's isomorphic to a summand in the Seiberg-Witten monopole Floer homology for the mapping torus. Okay. So, and it's somehow that is the promising thing, because it's saying that if you do this procedure of setting up this symplectic Floer theory in this space, what you get is indeed, Seiberg-Witten monopole Floer homology for that space plus a little bit of extra junk. So that's the principle that I would hope extends. Okay. Running out of time, but let me skip this. This is not so exciting. So how to prove that the -1 summand of stable pair Floer homology is the fixed point homology of Z? Well, Ivan Smith studied something very closely related. So he studied the blow-up of Cp to the 2g plus 1 along an intersection of two quadrics, and he used Lagrangian correspondences to embed the Fukaya category of a genus G surface into that of this blow-up. However, his result only applies when the genus is strictly bigger than 1. It does not apply to genus 1. So in the genus 1 case, there still is a Lagrangian correspondence which suggests that there ought to be a relation between the Fukaya category of this genus 1 surface and that of MZ. But this correspondence is obstructed. It doesn't induce a functor. And to get a functor, one would at least have to do something like this. One would have to deform this Fukaya category, perhaps by perhaps by making a bulk deformation. And it's not yet clear what deformation will actually make that work. Okay. So it's the obstructedness of this functor that means that we don't know how to use Lagrangian correspondence methods in this setting. So we do a more explicit calculation, and so for those of you who like Morse theory, so the following is our basic toy model, and I think this is sort of amusing. You can ask how do you do Morse theory on a blow-up along a complex submanifold of a complex manifold? So so x tilde is going to be the blow-up of a complex manifold X along a complex codimension 2 complex submanifold Y. So how to get Morse functions? So you can start with a Morse function on the base X, and I want to make it generic in the following sense. I want to assume that it doesn't have any critical points on Y. And furthermore, its restriction to Y is Morse. Okay. And now the thing that is a little counterintuitive is that its pullback f tilde to the blow-up is actually then not merely a Morse bot function, it's actually a Morse function. Why so? Well, on the exceptional divisor E, which is the projective normal bundle, f tilde has exactly one critical point, lambda y, over each critical point of the restricted function, f on y. What is it? It's the unique complex line in the normal space to y at that point, which is contained in the real three-dimensional space, which is the kernel of the derivative of f at that point. Okay, so that gives an efficient way of doing Morse theory on blow-ups. And so what we do is that, in computing this fixed point Floer homology on this blow-up of CP3, we we make a model for the relevant symplectic automorphisms, which as closely as possible mimics this toy model from Morse theory. So this gives us a way of computing fixed points. And thereby, well, essentially it gives us an upper bound on the size of fixed point Floer homology. There's an annoying snag with this approach, which is the following. To make it work, one needs to be able to use rather explicit symplectic forms on blowups. And that's easy to do when the weight of the blowup is low. So you're using a symplectic form which has small area on the exceptional spheres. But the trouble is we actually want to work with an anti-canonical symplectic form. Now, there are various ways that one could try and handle this discrepancy. The one that we have used is the following. There are continuity principles for Floer homology, which haven't been exploited very much. They're mainly due to Yi-Jen Lee, with also an input from Mike Usher, which give you circumstances under which one can see that Floer homology does not change in a one-parameter family. And so we had to make an argument to show that principle is applicable when one deforms the Kähler form from an anti-canonical one to a low-weight blow-up one. Okay, and okay, so right. So I think that's all I'll say about the proof. So where from here? Well, okay. So briefly, flip along in that sequence of flips, and it parameterizes extensions of it parameterizes those stable pairs where f sub phi is a holomorphic pair of the highest allowed degree, which in this case is g. Okay. The point here is that this locus is a PG bundle over sim g of z. So in other words, in this specific degree 2g plus 2, you have more or less a copy of sim g of z sitting there inside your space. More precisely, a projective bundle over it. So it's natural to guess, actually, that the stable pair Floer homology of phi always contains g copies of the fixed point Floer homology action on the g symmetric power. It really hints at a relationship with Heegard-Floer theory. In genus 1, it's also possible to get results in Lagrangian Floer cohomology. And again, one sees a relationship with Seiberg-Witten theory via Heegard splittings, so that's promising. The critical next step would be the construction of these Lagrangian submanifolds from Handel bodies. So that's something that I've been thinking about by means of degenerations of Z, but it's not a theorem yet. So, the conclusion is, if that can be done, one gets a well-defined Floer cohomology group from any Heegard splitting of a 3-manifold, and if it's invariant under stabilizations, one would get a potentially interesting 3-manifold invariant. Okay. Sorry for going over, and thanks for your patience.